Dear students, let's learn more about the electric dipole. When we place an electric dipole in an electric field, what happens? So that's what we're going to learn in today's class. So let us consider a dipole placed in an electric field. An electric field is represented by drawing parallel lines with equal spacing. So that represent uniform electric field directed as shown in the diagram with an arrow. Arrow indicates that the electric field is from left to right. In that electric field, there is an electric dipole. So you get to see, this is the center of the negative charge, the center of the positive charge is here, and the direction of the dipole moment is always from negative to the positive charge. And we are going to assume that direction of the dipole moment and the electric field makes an angle theta here. So this is theta. So what is the theta in the diagram? It is the angle between the direction of dipole moment, which is like this. This is the direction of the dipole moment. This is the direction of the electric field, and they make an angle theta. Theta can be 0 degree, 90 degree, 60 degree, any angle. Theta can be any. So we are going to assume that they make an angle theta. Now, in the presence of the electric field, what happens to the electric dipole? So that's what I'm going to explain. So let's consider a diagram of an electric dipole in an electric field. So this is the direction of the electric field, E. This is the direction of the dipole moment. That's vector P. This is vector E. This is vector P. And they make an angle theta. When a positive charge is placed in an electric field, it experiences a force in the direction of the electric field. So this positive center or center of the positive charge experiences a force in this direction, which is given by F is equal to EQ or QE. The negative charge also experiences the same force, F is equal to QE, but in opposite direction, because it's a negative charge. A negative charge experiences a force in a direction opposite to that of the electric field. That is like this. And now, these two forces, look at that diagram. So this is F is equal to QE. This is plus QE. This is center of the negative charge. Magnitude of the force is same, but the direction is opposite. And this is the direction of the electric field, and this is theta. What is the distance between the center of the negative charge and the center of the positive charge? That is called dipole length. That is a 2a. So, this is the center, this is A, this is A. That's total 2a. These two forces, they represent equal, unlike parallel forces, which represent a couple. And whenever a couple acts on a body, it always rotates the body. So this force tends to rotate the dipole in the clockwise direction. This force also tends to rotate the dipole in the clockwise direction, due to which this entire dipole rotates. And what do we call the rotational effect of the couple? That is called moment of the couple or moment of force. And that is what we are going to calculate in this entire derivation. So, what is the moment of couple, or is also called as the net torque, which I am going to denote that by a Greek alphabet tau. How to calculate the torque? Torque is given by magnitude of the force and arm of the couple. Now, what do you mean by that arm of the couple? Arm of the couple is nothing but the perpendicular distance between the forces. It is the perpendicular distance between the forces. To find that perpendicular distance, see, this is the perpendicular distance. This is the actual distance between the point of application of the force. We want this distance, which is here. So, BC is the perpendicular distance. So, tau is equal to force is F and perpendicular distance in the diagram is BC. F into. That BC we can write like this. See, this is a right angle triangle. Correct? BC by AB. BC by AB. BC is opposite side. AB is hypotenuse. So, BC opposite by hypotenuse is sine theta. So, this is equal to sine theta. So, BC is equal to AB sine theta. So, that is what I am going to write. So, BC is equal to AB sine theta. What is the magnitude of the force? Magnitude of the force is QE. Q into E. Into. What is AB? AB is nothing but the dipole length, which is a 2A. 2A sine theta. And Q into 2A is nothing but dipole moment, which is P and then E and then sine theta. So, this is the expression for a torque acting on a dipole, which is a PE sine theta. If you want to write the same in vector form, then vector tau is equal to vector P cross vector E. So, torque on an electric dipole is the cross product of dipole moment and electric field. So, this is the expression. And what is the result of this torque? The result is that this entire dipole, if this is a dipole, it's get rotated and it's get aligned in the direction of the electric field because of the rotation, because of the torque, it's get rotated and then it's get aligned in the direction of the electric field. So, this is the expression for torque experienced by an electric dipole in an electric field. So, expression is a tau is equal to PE sine theta, and in vector form, vector tau is equal to vector P cross vector E. If electric dipole moment is parallel to the electric field, then theta is 0 degree. Then the torque sine 0 is 0, so we get 0. So, torque is minimum. If the electric dipole moment is perpendicular to the electric field, theta is 90 degree, sine 91. So, torque is a PE and this is maximum. So, this is a 2 marks question. When electric dipole moment is parallel to the electric field, the torque is minimum, and when the electric dipole moment is perpendicular to the electric field, the torque acting on the dipole is maximum. So, now we are going to solve a numerical based on the electric dipole. So the statement goes like this: two charges 10 nanocoulomb and minus 10 nanocoulomb are separated by a distance of 0.1 meter. So first I am going to consider minus 10 nanocoulomb and plus 10 nanocoulomb separated by distance of 0.1 meter. 0.1 meter. Find the electric field, option A, at a point, midpoint of the line joining the two charges, that is here. At a point A. So this is the point A, which is the midpoint of the line joining the two charges. And then at point B, 0.1 meter away from A. So from A, at a point B, which is 0.1 meter away. This is the second case, point B. And on the side of the positive charge, And option C, at a point C, 0.1 meter from both the charges. So at another point C, which is at a distance of 0.1 meter from both the charges, from this as well as this. So these are the three different cases. So let's solve them one by one. So I'm going to consider the first one here. We need to find the field at this particular point. That is the midpoint of the line joining the two charges. So this is 0.1. This distance will be 0.05 meter. This is also 0.05 meter. So first I will find the electric field at this point due to each charge. So for that I am going to use E is equal to 1 by 4 pi epsilon naught Q by R square. 1 by 4 pi epsilon naught is 9 into 10 to the power 9 into the charge is 10 nanocoulomb. 10 nano, 10 to the power minus 9. So this will get cancelled here by the value of R is 0.05. Here R 0.05. That we can write it as 5 into 10 to the power minus 2. So square of it becomes a 25 into 10 to the power minus 4. So we have 90 by 25. 90 by 25. So 25 threes are 75, and then we have 15 left. So 150 means it's a 6 times. So therefore it's 3.6. 90 by 25 is 3.6 into 10 to the power 4. So unit is Newton per coulomb. Newton per coulomb. And the direction of it, here I'm going to consider this as a P and Q. So it's a positive charge, it's a negative charge. And if I place a plus 1 coulomb here, it's attracted. So the direction will be along AP. So that will be along AP. That's the field at A due to negative charge. Let us find field at the same point due to the positive charge. Okay. So this is E minus Q. And now I can find E plus Q, which is the same thing. 9 into 10 to the power 9. Magnitude of the charge is 10 nanocoulomb, 10 nano. Distance is still the same, which is 25 into 10 to the power minus 4. So our answer remains the same, 3.6 into 10 to the power 4 Newton per coulomb. And the direction of that is along. So if I place plus 1 coulomb plus repulsion, it will be in this direction. So it will begin along AP only. Along AP. There are two vectors are there now, E plus Q and E minus Q. E plus Q, E minus Q. They are along the same direction. So therefore the resultant is get added up, E plus Q plus E minus Q. Why does it get added up? Because when the two vectors are in the same direction, the resultant is a P plus Q. when theta is 0. So that's why we add. So on adding 3.6, you will get 7.2, and 10 to the power 4 is common. Okay, for both. So 7.2 into 10 to the power 4 Newton per Coulomb, and that will be along this direction, along AP. So this is option A. Now let's find option B. Option B. Option B is here, to find the electric field at point B. That point B is on the axis, and this represents an electric dipole, if you can see. So what is the expression for electric field at a point on the axis of an electric dipole? So E is equal to 1 by 4 pi epsilon naught 2 pr by r square minus a square the whole square. That is the formula for electric field at a point on the axis. So now what is a P, dipole moment, which is a Q into 2A. So what is the value of Q? Q is a 10 nanocoulomb. Q is 10 nano. 10 into 10 to the power minus 9. 2A is separation between the two charges, which is 0.1. So 10 into 0.1 is 1. So we get 10 to the power minus 9 Coulomb meter. That is the SI unit of electric dipole moment. So we have found P. What is the value of R? The value of R is this distance between the point and the center, which is already given, 0.1. So therefore the value of R is 0.1. So now let's substitute all these values. So 1 by 4 pi epsilon naught is 9 into 10 to the power 9. 2, the value of P is 10 to the power minus 9 into the value of R, which is 0.1. This power will get cancelled. Now we have to replace R square. R is 0.1. So 0.1 square is 0.01. 0.1 square is 0.01. Okay. Minus. What is the value of A? The value of A is this. So this is a 2A. The value of A is 0.05. So 0.05 square of it. A is 0.05 meter. So A square is 0.0025 meter square. So it is 0.0025 the whole square. So this will get 9 into 2 is 18. 18 into 0.1 is 1.8. It's 1.8 divided by 0.01 minus 0.0025. So let's use a calculator for that, and then we'll take the square. So we have 0.01 minus 0.0025 and then square. So on squaring we get 5.625 into 10 to the power minus 5. And when I divide 1.8 divided by 5.625 to the power minus 5. So when we divide, we get 3.2 into 10 to the power 4 Newton per Coulomb. So this is the final answer for the option B, where we get electric field at a point on the axis of a electric dipole. We have one more option, which is option C, to find the field at a point on the equatorial line. So what is the formula for field at a point on the equatorial line? E is equal to 1 by 4 pi epsilon naught P by R square plus A square to the power 3 by 2. Now if you see the diagram here, this is R, this is A. So this 0.1 is nothing but R square plus A square to the power half. That is according to the Pythagoras theorem. If this is R, if this is A, then this will be root of R square plus A square. So R square plus A square to the power half is a 0.1. We wanted r square plus a square, r square plus a square to the power 3 by 2. Which means I have to take the cube of this value, because r square plus a square to the power half is 0.1. R square plus a square to the power half is 0.1, but there is a cube. So which is same as 0.1 cube. 0.1 cube. 0.1 cube means it's a 0.001, which is same as 10 to the power minus 3. So this is the value of r square plus a square to the power 3 by 2. So now I can substitute here. It's a 9 into 10 to the power 9. The dipole moment is here, which is 10 to the power minus 9. That will get cancelled. Divided by 10 to the power minus 3. So therefore, when you simplify that, you will get 9 into 10 to the power plus 3 Newton per Coulomb is the answer to the third option. So hope you have understood, even though it's a lengthy problem, but all the three options are included here. One, finding the field in between the two charges, then finding the field at a point on the axial line of an electric dipole, and we have derived this formula in earlier classes, and then expression for electric field at a point on the equatorial line, that is perpendicular bisector of an electric dipole. So these problems are 5 marks question for the board exam. So you can use a calculator wherever required. And if the calculation is simple and easy, then avoid using the calculator. So we'll try one more numerical. Two charges plus or minus 10 microcoulomb are placed 5 millimeter apart. So minus 10 microcoulomb is one charge and the other is plus 10 microcoulomb is the other charge. They are separated by 2A, which is 5 millimeter. And Q here is this magnitude of Q is 10 microcoulomb, which is 10 into 10 to the power minus 6, which is 10 to the power minus 5 coulomb. And this two equal and opposite point charges separated by a small distance acts like an electric dipole. Determine the electric field at a point P on the axis of a dipole 15 centimeter away from its center O. So O is the center. At a point P, at a distance R, which is 15 centimeter. The value of 2A is 5 millimeter. The value of A is 2.5 millimeter. The value of R is 15 centimeter. Now what we get to notice here is this R is much greater than A, because this is in centimeter, this is in millimeter. That's why the given data is for short electric dipole. Since R is much greater than A, dipole is, it's a short electric dipole. So for short electric dipole, we have expression for electric field at a point on the axis, which is 1 by 4 pi epsilon naught 2p by r cube. The value of the dipole moment we can calculate. P is equal to Q into 2A. The value of Q, 10 to the power minus 5 into the value of 2A. 2A is a 5 millimeter. 5 millimeter. So which is 5 into 10 to the power minus 8 coulomb meter. 1 by 4 pi epsilon naught is 9 into 10 to the power 9. 2p, 2 into dipole moment is here, 5 into 10 to the power minus 8. divided by the value of R. R is given 15 centimeter. 15 centi, 10 to the power minus 2. And then cube of it, cube. So this we need to simplify. So first value here, so we have 5 into 2, that is 10, and 10 to the power 1 here, and 10 to the power 9 becomes 10 to the power 10. So this 9 into 10 to the power 10 minus 8 here, 10 to the power minus 8 will give you 10 to the power 2. Okay, so 5 into 2, 10, 10 to the power 1 we get, 9 plus 1, 10, 10 minus 8 is 10 to the power plus 2. Okay, and now in the denominator, that is 15 into 10 to the power minus 2. And then we have cube of that. We get 3.375 into 10 to the power minus 3. So now we need to divide that. So it's 9 into 10 to the power 2 divided by 3.375 to the power minus 3. So we get a value which is 2.667 into, we get the power 1, 2, 3, 4, 5 into the power 5 Newton per Coulomb. So this is the answer for electric field at a point on the axial line. Then we have another option B. Option B is given. A point Q. So we have another point Q here, which is 15 centimeter away from O. So R again 15 centimeter away from O. Normal to the axis of the dipole. Normal. So this is the axis. Normal means perpendicular to the axis. So at a point on the equatorial line, see, for same value for R is same in both the cases. Here also 15 centimeter, here also 15 centimeter. Then the ratio of the electric field at a point on the axial line to that at a point on the equatorial line is always 2:1. So therefore, electric field at a point on the equatorial line is half of the field at a point on the axial line. Field at a point on the axial line is this, 2.667 into 10 to the power plus 5 divided by 2, and that will you'll get 1.333 into 10 to the power plus 5 Newton per Coulomb. So that is the answer for the next option, that is option B. So it's very important to check initially whether R is comparable with A or R is much greater than A. If R is much greater, then we don't use the general formula as we have used in the previous case. We use the already modified version of the formula, which is a formula for electric field due to a short electric dipole, and this problem is related to electric short dipole. So hope you have understood about the electric dipole and the numericals related to it. So we're going to learn more concept in this particular chapter in the next class. And dear students, soon we are going to complete this particular chapter, and after that there will be a test in this particular chapter. So that's why I start revising this entire chapter. So a test will be conducted only in this chapter called electric charges and the fields. So the notes is already provided. So that's why I go through all the videos that I have put up in our channel and start studying especially all the 5 marks derivations, because only when you practice by writing you will be able to remember all these derivations. Okay. So I will continue the rest in the next class. Thank you.